Okay, next session is on multiple regression. To a number of topics. We'll cover the calculation of we'll get, the correlation matrix and the partial and semi-partial correlations, and then we'll also look at later in another video the calculation of the regression equation and the source table. The test data we have is made up of 3 variables: grade achievement on a standardized test, math achievement, once again on a standardized test, and reading achievement. And what I want to see is, in terms of academic achievement, in terms of the grade level on a standardized test for these students, 15 students, is math predict grade, and does reading predict grade? I could run these as 2 simple regressions, but I want to run them together, so I want to see what each uniquely contributes to the regression equation. Okay, first thing to do, I want to look at the correlations amongst the variables, and this is the function, the analyze, correlate, bivariate. I pick my 3 variables, and here we go. The data, this is the SPSS data. Here is the, just from Excel, my 3 variables, grade, math, and reading, and then grade, math, and reading. I've duplicated here. The 1s represent the diagonals, and really the correlation between grade and grade is 1, math and math is 1, and reading is 1. So I think basically it just correlates with itself. It's a bit redundant, but it is in matrix form, which is for basically a different form of algebra. The correlation between grade and math is 0.912, and the correlation between grade and reading is 0.676. So math has a higher correlation with grade than does reading, and then the final correlation is the 0.753, and that's the correlation between math and reading. And that represents to some extent what might be a problem. I want to see, what does math predict grade and does reading predict grade, but what do I do with the shared variance between math and reading? Because clearly math performance is related to reading performance. The bottom is a correlation matrix produced from SPSS. Same format, just a little uglier. It's got tests of significance, and it gives you the ends. And one thing here, the yellow here, I've talked about, but the blue is just redundant. It's just the mirror image of here. So 0.912, 0.912, 0.676, 0.676. So it truly is redundant. It's just putting it in square matrix form. Now, what I want to do is I want to predict grade, and we're using as my predictors reading and math. So my independent variables are reading and math, and my dependent variable is grade. The total sum of squares for grade is made up of the areas under this circle here, within the circle. So the area F, A, B, and D. F is the part of grade that is not explained by either reading or math. So it is basically, would be in a sense, my residual. A and B represent the overlap between reading and grade. So that would be my shared variance. That would essentially be my R squared between grade and reading. The R squared between grade and math is the B and D added together. So my B and D over the total sums of squares for grade represents the shared variance between grade and math. My problem is, what do I do with the B? The A represents that element of reading that uniquely predicts grade. So that is only reading. That's the variance for reading that is uniquely shared with grade. Similarly, D is the unique variance for math that is shared with grade. The B, which is the overlap of the 3 circles, in this case, when I look at it from the perspective of reading, it is that part of reading that is shared with grade, but is also shared with math. Conversely, for math and grade, B is that part of math that is shared with grade, but overlaps with reading. So I kind of look at it 2 ways. So what I want to do is I want to figure out that area of A that is unique to predicting reading. So what part of reading is predicted that uniquely contributes to the prediction of grade? And in terms of a test of significance, that's what I want to see. So if my slope function is significant, I want it significant because that element of reading that uniquely predicts grade is what I want to see. And it basically says, yes, reading uniquely and on its own predicts grade. Similarly, D, I would want to see D over the sum of A plus B plus D plus F. Say, well, what does math uniquely on its own contribute to a prediction of a student's grade? This calculation here is referred to as a semi-partial or part correlation. And what it is, I'm separating out the B to figure out what is a unique predictor, in this case, say for math, over as a ratio of the overall variability for grade. And that's referred to as a semi-partial or part correlation. So if I look here, the calculation for the semi-partial or part correlation, I'm using 1 and 2. So variable 1 is grade, variable 2 is math. So what is the shared variance between grade and math, partially out of removing the influence of reading? So that's that D. What is uniquely math that predicts grade? It is the correlation between math and grade, subtract the correlation between grade and reading, and the correlation between math and reading, all over 1 minus the r squared, which is the correlation, r squared, for the relationship between math and reading. And that's what's left over. I perform that calculation, and the semi-partial or part correlation for grade and math controlling for reading is 0.612. But what I can see happens is the correlation between grade and reading, controlling for math or eliminating the influence of math, is negative 0.015. So in terms of the semi-partial or part correlation, the correlation between grade and reading disappears when I control for the influence of math. So that means that reading on its own is not a very good predictor, or does not predict grade. Whereas math, when I control for reading, the partial correlation still would be significant. It drops, but it is from 9.12 down to 0.612. The other correlation is, we just looked at the part or semi-partial correlation. There's also what's referred to as the partial correlation. The only difference between the partial and the part correlation, terms gets a little confusing, is the denominator. The denominator for the partial correlation is A and F. So what you're doing is you're basically chewing off math completely out of the equation here. So I just want the relationship between reading and grade, but only that which is shared between reading and grade, and that which is uniquely F, that is not predicted by either variable. So it's A over the r squared for F and A. This means that for a partial correlation, the r squared, or r, will be higher than that seen for the semi-partial. And the reason is the denominator is different, is lower, is smaller. So it's r, the F and the A, which produces a larger correlation. And this is the formula right here. So the r, the formula is and I'm doing math, grade and math. So the correlation between grade and math minus the correlation between grade and reading, and the correlation between math and reading, all over 1 minus the square root of 1 minus the r squared for grade and math, minus multiplied by 1 minus the r squared for math and reading. Just to be clear, so this is the 1 minus the r squared for grade and reading, multiplied by 1 minus the r squared for math and reading. And I take the square root of that. That will produce my semi-partial correlation. my partial correlation. Sorry, and that's where the denominator is just the unique variance for grade and that which is shared between grade and math. And I similarly have the same thing for grade and reading, controlling for math. As you can see here, if I flip to the slide, correlation of the semi-partial part, because it has the larger denominator, 0.6 and negative 0.015, compared to 0.83, which is less than the 0.9, and negative 0.03, which is less than the negative 0.015. So I have the smaller denominator. Okay. So if I have this in Excel. So here's our data in Excel. The spreadsheet's uploaded to the course Blackboard. And once again, here's my correlation matrix. I walk through here the calculation of the partial correlation, which is, here's the 0.83 and the negative 0.0376. And then I have the semi-partial correlation, the 0.612 and the negative 0.015. So this value here is less, this value here, the semi-partial, is less than the partial, because the partial has a smaller denominator, and the negative 0.015 is less, in terms of closer to 0, than the negative 0.03. Okay, and that is the, you can work with this spreadsheet in terms of other correlations. That is the relationship between the partial correlation and the part correlation. And once again, the purpose is to deal with my problem here. What do I do with this B? I want to isolate it out, and I want just that which is shared, which is the reading and grade. The partial correlation has the smaller denominator, right? It's only the F and the A, whereas the semi-partial correlation has the whole in terms of the total sum of squares, or R's, for grade.